The graphs of the function g and f are shown in the figure where x ranges from 0 to 3. The twice differentiable function f satisfies f of 3 equals 2, and the integral from 0 to 3 equals 10. G of x is equal to 12 over 3 plus x. Find the area of the shaded region enclosed by f and g. Evaluate the integral from 0 to infinity of g squared dx. And then find the integral from 0 to 3 of h of x. So first we're going to find the area of the shaded region enclosed by the graphs of f and g. This will be the integral from 0 to 3 of f of x minus g of x. And that's because f of x is greater than g of x on this interval. Now we can split this integral up using linearity. The integral from 0 to 3 of f of x minus the integral of 0 to 3 of g of x. That first integral is equal to 10, given to us in our problem. So now we substitute for g of x 12 over 3 plus x. And that's the integral we have to evaluate here, using a little u substitution. We'll let u equal 3 plus x, and therefore dx is going to be equal to du. The limits of integration will change here from 0 to 3 to 3 to 6. The integral from 3 to 6 of 12 over u du evaluates to 12 times the natural log of 2. Alright, so part A, we have found the area, and we can evaluate that using a decimal approximation. The area is approximately 1.682233, or 1.683. In part B, we're trying to evaluate the improper integral from 0 to infinity of g squared, or show that that integral diverges. Plugging in g and squaring it into our integrand, we get the integral from 0 to infinity of 144 over 3 plus x quantity squared. Again, we're going to treat this with a u substitution. We'll let u equal 3 plus x, du will equal to dx, and that'll give us new limits of integration from 3 to infinity. So the integral is from 3 to infinity of 144 over u squared du. That will evaluate to negative 144 over u from 3 to infinity. And when we set this up using the fundamental theorem of calculus, 1 over infinity evaluates, or the limit will go to 0, and that'll just give us negative 1/3 inside there. So negative 144 times negative 1/3 is positive 144 over 3, or 48. So part B evaluates to 48. In part C, let h be the function defined by x times f prime of x. Evaluate its integral from 0 to 3. In this case, we're going to want to employ integration by parts. We look at the integrand as u dv, so we'll let x be u and f prime of x dx be dv. Differentiating and integrating those two parts, we get du is equal to dx and v is equal to f of x. So by the integration by parts formula, we get x times f of x evaluated from 0 to 3 minus the integral from 0 to 3 of f of x dx. That second integral was already given to us as a value in the problem, and f of 3 as well is given to us. So f of 3 is equal to 2. 3 times 2 is 6. 6 minus 10 is negative 4. So the value of this integral is negative 4. Well, that was part 5 in the BC Calculus exam. Next, we'll explore question number 6 in the BC exam. The function f has derivatives of all orders for all real numbers. It is known that f of 0 is 2, f prime of 0 is 3, and f double prime and f triple prime are given here. We have a few things to find involving the Taylor polynomial expansion, and in this case, the fourth degree polynomial expansion. So first we'll have to find the fourth derivative approximated around x equals 0. Then we'll have to do an error-bound approximation. And then we're given a function g of x, or g prime of x, to which we are to write its second-degree Taylor polynomial about x equals 0. Alright, so let's see how this one goes. Part A, find the fourth derivative of f with respect to x. Write the fourth-degree Taylor polynomial of f about x equals 0. So differentiating the third derivative with respect to x will give us the fourth derivative with respect to x, here noted by f superscript 4 of x. Because f triple prime is given by a product, we will have to use the product rule to differentiate it. So there's a product of negative 2x and f prime of x squared. By applying the product rule, we get negative 2 times f prime of x squared, and that's going to be added to negative 2x times the derivative of f prime of x squared, which is f double prime of x squared multiplied by 2x. We can clean this up a bit. f4 of x, or the fourth derivative of x, is negative 2 f prime of x squared minus 4x squared f double prime of x squared. There's our fourth derivative, and that will be useful in helping us write our Taylor polynomial expansion that is an approximation for f about x equals 0, and when it's about x equals 0, it's called a Maclaurin series. So in general, this will look like f, and we'll call this f sub 4 for the fourth order Taylor polynomial approximation. And that's going to be f of 0 over 0 factorial plus f prime of 0 over 1 factorial x to the first plus f double prime at 0 over 2 factorial x to the second, and we'll work our way down to the fourth derivative over 4 factorial x to the fourth. So we have our fourth degree polynomial. Now in a Taylor expansion, the derivatives as well as those divisors of factorial numbers, those are going to give us our coefficients of our Taylor polynomial. That first piece will give us 2. F prime of 0 is equal to 3, so we'll get 3x here because 1 factorial is equal to 1. F double prime of 0, well, we have to evaluate that using what they gave us here. And that looks to be equal to negative f of 0, or negative 2. And negative 2 divided by 2 factorial is just negative 1, so that third term is just negative x squared. The third order term, we have an expression for f triple prime, and we'll evaluate that at 0, and that's going to be 0. So that third order term drops out. And last but not least, we'll use our fourth derivative we calculated to find the coefficient of the fourth order term here by plugging in 0. And that looks to give us negative 6. Now dividing that by 4 factorial will give us a negative 1/4 x to the fourth as our final term in our fourth degree Taylor polynomial approximation. So there it is, part A finished. So now part B. The fourth degree Taylor polynomial of f of x about x equals 0 is used to approximate f of 0.1. Given that the absolute value of the fifth derivative of x is less than or equal to 15 on the interval from 0 to 0.5, use the Lagrange error bound to show that the approximation is within 1 over 10 to the fifth of the exact value of that function. So now the Lagrange error bound can be defined as the maximum value of the fifth degree or fifth order derivative evaluated at that on that interval, so at a value for which it takes on a maximum, then that's divided by 5 factorial and multiplied by 1/10 to the 5th power. Basically, this is the 5th order term in the expansion for the Taylor polynomial approximation. We're told that the absolute value is less than or equal to 15 for that 5th order term. So we can replace the max value of the 5th derivative with something that is less than or equal to 15. So we'll put 15 over 5 factorial, and then 1/10 as a fraction to the 5th power is 1 over 10 to the 5th. Now that coefficient in front of 1 over 10 to the 5th, in other words 15 over 5 factorial, can be simplified pretty easily. And that's going to evaluate to, let's see, with a little cancellation here, 1 over 8 times 10, 1 over 10 to the 5th. And that there is clearly going to be less than 1 over 10 to the 5th. So by Lagrange's error bound, we have shown that the approximation is within 1 over 10 to the 5th of the exact value of f evaluated at 0.1. So in essence here, the Taylor approximation error can be found in the next order term. Since we found a 4th degree polynomial, the 5th order term is where we can find the maximum amount of error that we can calculate. So if we use a 4th degree approximation, then the error will be found most significant in the 5th order term. And that is why they use the 5th derivative in this particular Lagrange error bound. Now C says g is the function such that g of 0 is 4, g prime of x is e to the x times f of x, and we want the 2nd degree Taylor polynomial for g about x equals 0. So g sub 2 would be g of 0 over 0 factorial plus g prime of 0 over 1 factorial times x plus g double prime of 0 over 2 factorial times x squared. G of 0 is equal to 4, and g prime of 0 by evaluation is e to the 0 times f of 0. Since f of 0 is 2 and e to the 0 is 1, we get 2. G double prime will be found by differentiating g prime using the product rule, and that'll give us e to the x f of x plus e to the x f prime of x. By evaluation of g double prime at 0, we get e to the 0 f of 0 plus e to the 0 f prime of 0, or 2 plus 3, which is 5. So now plugging into the polynomial approximation, g2 of x is equal to 4 plus 2x plus 5 over 2 factorial, which is 5 halves, x squared. And that's our 2nd degree Taylor polynomial for g. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. Thanks for watching.